As we have seen, the commutation relation between the various components of the angular momentum operators relevant to a quantum mechanical system depends solely on the geometry of rotations. So it does not matter whether you have orbital angular momentum or spin angular momentum or some other version of angular momentum. The commutative of Jx and Jy is always I h bar times Jz, and the other commutation relations follow cyclically. Now, in your previous quantum mechanics course, you must have learned how to find out the eigenvalues and eigenvectors of angular momentum operators. In particular, you have seen that J square, Jx square plus Jy square plus Jz square commutes with Jz. In fact, it commutes with Jx and Jy as well. So J square and Jz commute so that they can have simultaneous eigenstates. Of course, there is nothing special about Jz. It could have been J square and Jx or J square and Jy. What you could not have had are simultaneous eigenstates of Jx and Jy, at least not a complete set of them. So what we look for are simultaneous eigenstates of J square and Jz. And as you all know, the eigenvalues of J square are quantized. They are J into J plus 1 h bar square, where J can be either a half integer or an integer. So allowed values of J are 0, half, 1, 3 halves, and so on. On the other hand, the eigenvalues of Jz are m h bar, where m takes values in integer steps from minus j to plus j. So the ket Jm denoted here is a simultaneous eigenstate of both J square and Jz corresponding to the eigenvalues I have just mentioned. In addition to this, we know that there are ladder operators J plus minus which are formed by taking combinations, non-Hermitian combinations of Jx and Jy, Jx plus and minus Ijy respectively, whose job it is to raise or lower the m eigenvalue or the Jz eigenvalue. So J plus Jm gives you a state which is proportional to Jm plus 1, J minus Jm gives you a state which is proportional to Jm minus 1. And in your previous quantum mechanics course, you have definitely learned how to find out these normalization factors, in root over J minus m into J plus m plus 1 and so on. So, to sum up, for a given J, the states Jm where m runs from minus J plus 1 all the way up to plus J form what is called an irreducible representation of the rotation group. Now that's quite a mouthful. So let me break down what this means. It simply means this: you take any of these states Jm for a fixed J and see what happens to it under the rotation of coordinates. What happens to it is that it becomes a linear combination of Jm primes, where the m primes may take any value from minus J to plus J, but the J index stays exactly the same. So put simply, when you rotate your coordinates, the Jm's only mix among each other, and in a mathematical form what we can write is the action of rotation of coordinates on Jm is of course the operator un hat theta, the rotation operator, acting on the ket Jm, but the resulting ket is a linear combination of Jm primes where m prime runs from minus J to plus J. The coefficients of this linear combination, despite the complicated appearance, this is really nothing but a number, or at least one number for each m prime. Well, they together define the matrix for the rotation operator, corresponding to the rotation operator, and it's a standard terminology to write this as dj m prime m n hat theta. I'm pretty sure in your previous linear algebra courses you have learned why the coefficients of dj are dj m prime m and not what might seem more natural, dj m m prime. So basically what you do is you apply un hat theta on Jm, realize that the resulting vector is a linear combination of Jm prime, take the coefficients of that linear combination and use those coefficients not to write down the mth row of your representation matrix, but the mth column. So the coefficients go column wise. This I am pretty sure you have learned in a previous course on linear algebra. And you must have also learned the reason. If you do this, then the matrix corresponding to two successive transformations end up being the product matrix for the two different matrices. Now, this tells you that the set of all Jm's taken together form a representation of the rotation group. What that means is when you apply any of the rotations, you end up with a combination of just these vectors Jm. So all other vectors that may be there in the vector space, they don't enter into this set of linear combinations of Jm, which is the span or the linear vector space spanned by Jm for all the m's from minus j to plus j, actually is an invariant subspace when you rotate. That is, take any vector in this subspace, you rotate your coordinate system, the result is a vector in the same subspace. So that's what representation really means. Irreducible simply means that this is the smallest bit that does the job. Any subset, any proper subset of this collection of linear combinations of Jm does not have this property. So while the space spanned by Jm, m going from minus j to plus j, is an invariant subspace, the fact that no proper subset has this property of invariance is exactly what is meant when you say that the representation is irreducible. Once again, this lapse into group theoretical language can be ignored. All you need to know is when you rotate eigenket of j square and jz, you get a linear combination of eigenkets of j square and jz with the same j square eigenvalue but different jz eigenvalues. And this combination gives rise to so-called rotation matrices, whose properties we are going to see later. So, of course, how many such coefficients do you get? You have 2j plus 1 possible m values from minus j to plus j, and for each one of them you have 2j plus 1 corresponding m prime values. So this dj m prime m actually form a 2j plus 1 by 2j plus 1 matrices, a matrix. So these matrices, one actually for each n hat and theta, so infinitely many such matrices, they form the rotation matrices for spin j.